It is difficult to overstate the importance of the central limit theorem for the impact on our ability to make meaningful inferences about the parameters of a data set. The implications of the central limit theorem go well beyond what we gain from it. They touch virtually all branches of mathematical statistics, theoretical physics, chemistry, and other disciplines. What we have learned is that when we calculate a mean of a sample, we should think of this mean as simply an observation, like other observations. But we know this observation comes from a normal distribution, and the mean of this distribution has a mean equal to the mean of the population. It is this mean of the population that we are interested in knowing. This conclusion is unchanged regardless of the actual distribution of the population data. We have also set the foundation for expanding the central limit theorem beyond the sampling distribution of means. There is a sampling distribution for sample proportions. We should not be surprised when we discover that this sampling distribution is also normally distributed. We have also learned the relationship between the sample size and the standard deviation of the sample distribution. We know that the sampling distribution standard deviation decreases as the sample size increases. The central limit theorem concludes that the standard deviation of the sampling distribution is sigma divided by the square root of n, the sample size. As the sample size increases, because it is in the denominator of the standard deviation of the sampling distribution, it causes the standard deviation to decrease. Finally, we have developed this finding into an understanding of why size actually does matter. For sample size, anyway, at least in statistics. A sample mean from a large sample has a narrow range of possibilities for the true population mean at a constant probability. This comes from the central limit theorem and forms the basis of our next assignment, estimating a population mean from sample data. This relationship will provide us with a probability as to the accuracy of our estimates. This results in what we will call our level of confidence in the estimate. All this from the central limit theorem.